Hello and welcome to this new video where we discuss mathematics and physics on the board. Today what we are going to discuss is the Legendre transformation. Often this is kind of pushed onto students as a simple, as an algorithm basically, but not necessarily like by explaining what it actually does. And that's what we are going to see today. Right, okay, so let's set a little bit the stage for Legendre transformations. So what we want is basically a function f, so that's a map that goes from the reals onto the reals. Okay, at least we are going to limit ourselves to that, okay? And so it's going to take a real x and then return another real f of x. Now, traditionally, the way you're going to graph that particular function is basically by taking a Cartesian kind of plane with x being on the what is called x-axis, right? And then representing the f of x here on the y-axis. Okay, so that's how you graph a function. And so here in black, for example, I represent a curve that is basically looking like a parabola. Okay, now that's actually an important property that we want to take on board here, that is satisfied by parabolas and tons of other functions, is basically that we want here the function to be convex. In later videos, we are going to see what happens if the function is not convex, but for the time being, what we want is the function to be convex. So if the function is convex, what that means, and that the definition here, is that the second derivative of f is actually positive, and strictly positive to avoid any ambiguities, and for any x on the real line. Okay, so here at least that's what I'm going to work with. So we have a function f, and this function f is actually convex, meaning that it has its second derivative, which is positive for every x. Now, if the second derivative is positive everywhere, what that means is that the rate of change of the derivative is actually positive everywhere. So another way to say that is that f prime of x, the derivative of x, is actually monotonously increasing. So sometimes people say it's a monotonously increasing function. Now, if you have a function that is monotonously increasing, so it's always increasing and never like plateauing or never going down, then what that means is that basically you can create a one-to-one relation between the f prime of x and x, okay? Because for any, maybe I can draw it here, if you were to draw it on that particular axis, you've got x here, and let's say here you've got some f of x. Okay, so here I've almost plateaued, but imagine it's increasing a little bit. So essentially here, just to be really much clearer than that, because this part here is a bit dubious. So let's say we are going to have things like that. Right? So it's always kind of increasing, even if it's kind of wobbling about. So this is f prime of x, and what that means is that you can have, for any x here, you can have a corresponding increasing f prime of x. Okay, and you can actually view that the ordering is going to be the same. So let's say here this is x1, here this is x2, and if x1 is smaller than x2, then so f prime x1 is going to be smaller than f prime x2. And basically you can get this one-to-one relationship here. So that's what I'm describing there. Now, why is it that we care about this one-to-one relationship? Well, this is represented on this diagram here. I've basically drawn some tangent lines to the curve, okay, to the graph of f of x. So on the right-hand side, I've drawn two tangent lines. I've kind of messed up here, but you need to imagine a tangent line here, another one there, and I've done the same as well too on the left-hand side of the curve. Now, because these are tangent lines, and the tangent lines have a slope, which is a derivative of basically the function at that particular point, then basically what I can say is that for any point, basically you're going to have a unique tangent line, okay? And that's what matters, is basically we are going to get that this relationship x corresponds to f prime of x. It basically means that there is a unique correspondence between x and then the slope of the tangent line. At x, okay? And that's actually what we are going to use. So let's be a bit more specific here. We are going to say that we denote, let's say P, and P we are going to say it's equal to f prime of x, and that's the slope of f of x at x. Okay, so that's the first thing we do. Now, because we have a one-to-one relationship, so what I can also call a bijection, then it means that the inverse of f prime actually exists. So what I can have is that one-to-one tells us that x, if you know p, the slope, you know that x is equal to f prime minus 1 of p. Okay? So that's, again, here I'm basically stating facts. Once we have said that, then what we say is the following. We say that the equation of a tangent line at x, what is it? Well, basically this is f of x. And what I'm doing here is that I'm writing the on the left hand side I'm writing f of x, and then on the right hand side I'm writing an approximate sign, basically because I'm using a Taylor expansion here. So here you've got that f of x is going to be f. That's not a good way of putting it. So let's say here equation of tangent line at x naught. Let's say we've got some x naught. Then what you have is that you use that f of x is approximately equal to f of x naught, and then plus f prime of x naught, and then x minus x naught. Okay, and this thing here is the equation of the tangent. Okay, so that's the equation of the tangent line. Because it's linearly increasing with x minus x naught, which is what you expect from an equation of line like this. Now, what you want is to express that as basically a function that is f prime of x naught times x. So you want to express that as px plus basically a constant which is the intersect at the origin. That's the equation. That's the definition of the equation of a line, right? So intersect at the origin. Okay, and so what you have is that basically the p times x is actually f prime. So I still keep it there. So that's p. Let's call that p0 because that's corresponding to x0. I've got p0 x, and then I've got plus f of x naught, and then minus P0 x naught. Okay, so here, this is basically, remember, if you write y equals ax plus b, basically here, this is a, and the b is actually all of that. Okay, so that's basically what I'm representing. Now, where am I going with this? This is the equation of a tangent that is at any arbitrary x naught. Okay? And so what we are going to do is the following. We can create a duality between a representation of the function f that relies on basically x, you give x and f of x. So that's a particular representation where you give the value of x here and the corresponding height, if you will, on this graph. Fair enough. And the other one that you can actually put forward is you give the slope. Okay, you can give the slope p of your actual of a line at a given x. Okay, so you give the slope, but the slope is not enough. You need to know the equation of the full line. But the equation of the full line is going to be characterized by two things: the slope and the intersect at the origin. And this is actually this quantity here. And actually, what we are going to call that is basically f star of x naught. And in fact, what I'm going to do here is f star of p. Okay, you see, I've got x, f of x, and here I've got p, f star of p, and the interpretations are as follows. Here, this is basically kind of the some original variables. So let's say, I don't know exactly how to call that. So let's say original argument. And then that's the height of f of x that you would represent on the graph. And then basically this here is set of, so that's a slope of a tangent line. And then this slope is also uniquely related to an intersect point. And so that's the intersect. At the origin. And I'm going to provide basically that's kind of the equation. So you've got this duality where you can decide to represent your function, the action of the map, in two different fashions. And these are always a pair of numbers, a set of pairs of numbers. Either you provide x and f of x, okay? Or you provide equivalently in another kind of universe, if you will, a dual universe, from the reals onto the reals, p, f star of p. And graphically, again, one is representing x versus the height of the graph, and the other one is representing a set of straight lines that basically are going to be the to cover the entirety of the graph if you were to plot all of them, okay, at every single point. And in fact, that's how some people in antiquity used to draw fantastically beautiful curved geometry via straight lines, okay? That's precisely by using this particular duality between straight lines and basically correspondingly curved basically graphs. Okay, now it turns out that this f star of p is what we call the Legendre transformation. Okay, so it means that now what we care about is we give a range of values for the slope, and that's p, and then we call f star of p we say that's the intersect of that slope. And if you were to plot all of them, you're going to obtain, at least alongside this particular graph, then you're going to draw the graph itself. So that's basically what the Legendre transformation is. So I'm just going to erase here, and basically I'm going to formulate that a bit more properly. Okay, so we can resume. So here we've got f convex, etc. And now what I'm going to do is that I say then that we've got a set of P. So P, which is equal, remember, to f prime of x. Then, in fact, you say that for any P in R, or at least in the domain that is supported for P here, you're going to have f star of P is equal to, and the way it works is basically I'm reading off this. So that's actually f of x naught, f of x minus P and then of x. So you could say, well, hold on, I don't get it. Like, why do I still have x's here? Actually, I shouldn't have the x's. That's just how it works. And then what you need to specify here is that the x is evaluated as being f prime minus 1 of P. Okay, that's a super crucial step. You need to substitute the x once you have written that. You need to substitute x with the actual f prime minus 1 of P. Okay, and this thing here is what we call the Legendre transformation. So again, you provide a slope, and this equation is going to give you essentially the values of all the intersects of these tangent lines, and given every possible slope, and then you're going to get all the possible slopes covering this particular curve here. So this is the Legendre transformation. And we can try to look very quickly at an example. I'm not sure if I will have enough space here, but let's try out. In any case, in worst case scenario, I'm going to erase on the right-hand side. So let's try f of x is equal to, let's say just x squared. Okay, let's take it easy. So we take f of x is x squared. That's roughly what I attempted here anyway. So f of x equals x squared. The first thing we need to do is actually say, well, f prime of x is equal to 2x. Okay. Now remember that what I want is basically that means that if I substitute f prime of x by p, I've got that p is equal to 2x, and therefore I've got that x is going to be equal to p over 2. So if I've got a certain value for p, I need to divide it by 2 to actually get the value of x. Okay, that's quite interesting. What we see is that the derivative is simply proportional to x. Okay, so now I basically have this part of the problem, which is x, to be expressed as a function of p here. So that's the first step, and then basically I apply that equation. So f star of p is equal to, so f of x we said was x squared, and then minus p x, but then I need to evaluate when x is equal to p over 2. So what that means is that I've got here p squared over 4, okay, and then I've got minus, and then I've got p times p over 2. And so what I get in this particular instance is that this is equal to minus p squared over 4. So we can try to see if it works. So for example, what we want is an intersect. So let's say we take whatever we take, actually P negative or positive, what we are going to see is that they are going to intersect at the same location. So let's say you take P is equal to 2, so you've got a slope of 2, and then you know that the intersect of that slope has to be basically there. Now, interestingly, in this particular example, what that means is that if you have a particular convex function, then the Legendre transformation is going to be concave. Okay, so here you see it's minus p squared over 4. And basically we're done. Okay, so that's basically calculated. And the function is going to be concave. And that's one of the properties of it. Now, there are some ways to formulate it in such a way that you preserve kind of the concavity and convexity. But in this particular example, we have, in terms of slope, then that's what we have. Okay, the intersect is going to correspond to a concave function of the slope. All right, so that's basically how it works. We are going to see in some further video how it actually is applied in kind of Lagrangian mechanics, for example, and also in thermodynamics. If you've got any questions or comments or some aspects that are not clear about what we have just seen here, by all means, do let me know in the comment section, and I would be happy to expand some of the explanations. Otherwise, see you in the next video.